Welcome everybody to session number 5 of the Fuel Educate series. Today we are joined by another speaker from Fuel Labs, David, who's coming up to the stage right now, and who will be telling us something about predicates on fuel. So everybody feel free to say hi to David in the chat, and if you have any questions, the usual, put them in the chat or in the questions tab, and David will get to them later on. David, the stage is yours whenever you're ready.
Sounds good. Hey, everybody. Great to be joining you guys today. Yeah, I'm excited to talk about predicates, which I think is kind of one of the superpowers of fuel, one of the kind of most interesting, but also sometimes hard to understand components of the fuel stack. So yeah, I'm going to take a shot at explaining what they are, why I'm so excited about them, what's so cool about them. Let me just share the screen really quick. There we go. I think you guys can see everything, right?
Yep, perfect.
All good. Cool. Yeah. So as I said, my name is David Mihal. I'm going to be talking about. Okay, so sorry, just there we go. Now I'm all set up. Yes, I'm going to be talking about predicates, which are, in my opinion, one of the coolest things about Fuel. Yeah, quick background on myself. I'm a senior architect at Fuel. Been kind of part of the contributed to the project since the beginning, and now kind of working on product architecture and just high level direction at Fuel. So I want to talk to you guys about why predicates are so cool, why they're the new contracts, the new smart contracts, how predicates can potentially replace smart contracts someday, and you know, most importantly, why they're important. So to start with, kind of what is the problem we're addressing? The issue we're trying to address with predicates is that blockchains are getting heavy. Blockchains are getting, blockchains are always growing, but specifically the state of blockchains is getting really heavy. We've run some numbers of looking at kind of the size of state of various blockchains of Ethereum, Polygon, Base, whatever. And generally speaking, the state of blockchains, kind of grows indefinitely. And as we're coming up with new higher performance blockchains, as we're coming up with rollups and things like that, we're actually making this problem even worse. Blockchains are growing even faster and faster. You can see on this chart here, Ethereum is the one in blue. Ethereum's been kind of growing at a pretty even tick since 2017, when it really started to take off. But we can see these newer blockchains like Polygon and Binance Chain, and the newest one on the bottom right there is Base. The state of these chains is growing, and they're growing rapidly. Even chains like Base, which are new, which are rollups, which are supposed to be kind of solving a lot of the issues with Ethereum, are kind of growing at a state that's quite unsustainable. So why is this a problem? What happens when a blockchain gets heavy? Specifically, when the state of a blockchain grows really large, it becomes really hard to run a full node on a blockchain. Got here a tweet from Peter. Peter is kind of the lead of the Geth team, the Go Ethereum client team, and Peter's been a loud voice talking about how state growth is the biggest problem in scaling Ethereum. It's not really transaction execution. It's not the consensus mechanism. It's that the state of Ethereum is really big. We want to keep Ethereum able to run on a certain type of computer. We don't want to kind of become, Ethereum to become a Solana that can only run on data centers. And therefore, it's really state growth that's constraining the growth of or the scale of Ethereum. So we see this cycle kind of happening over and over again in the blockchain ecosystem as chains become heavy. Most blockchains are cheap in the beginning. You get, Bitcoin used to be super, super cheap. Ethereum came out. Ethereum talked about being the cheap chain. A lot of these new, rollups and other chains we see today talk about, oh, we're the cheap chain. And then they're cheap until they become popular, until people start using them. And then the chain kind of starts to reach its capacity, the fees start to grow, and people say, well, it's okay that it's expensive because it's popular, it's a big success. And once this becomes a sustained part of that chain, these chains tend to kind of pivot towards being a layer 2 or a layer 3 or something like that, basically saying, this chain is going to stay expensive. You should build other things on top of this chain. So what we really want to do is to break this cycle, because we've seen all these chains are growing, and they're growing at a rapid pace. So how do we break this cycle? How do we make blockchains that are more sustainable? How do we make chains that don't grow as quickly? The really tough thing about how we address this is we need to change the way we build applications. This is unfortunately not something that you can just slap on a new piece of technology onto. A lot of times blockchains get rollups that are somewhat transparent to users, transparent to developers. Addressing the state growth issue is not going to be a straightforward solution, because it's fundamentally changing how we think about applications on blockchains. So I'm going to jump into kind of talking about how we're addressing this at Fuel, but I want to do like a little bit of a history lesson first. So let's rewind and go back to the original blockchain and look at how it works. We're going to talk about Bitcoin. So Bitcoin only has really two types of entities on Bitcoin, on the chain itself. Bitcoin has coins. These are the UTXOs that make up Bitcoin, and it has accounts. Really, the accounts are just the owners of these coins. And yeah, that's kind of it. That's all that's really stored by a Bitcoin node. However, there are two different kinds of accounts on Bitcoin. We're mostly familiar with kind of public key type accounts. I think most blockchain developers understand that typically your blockchain address is derived from your public key. And when you spend your coins, you sign a message with your private key. So you keep your private key on your computer, you share your public key or your address, which is derived from your public key. And then with your private key, you can sign messages to send those coins. However, Bitcoin has a separate type of account called scripts. This was introduced to add more functionality to Bitcoin. That instead of just having an address, you could create a script, and that script would do something like maybe it's a multi-sig. It's going to check, are 2 out of the 3 signatures I need available? Simple script. Or you can do lock contracts. You can do payment channels, things like Lightning Network. So any of these extendable functionalities of Bitcoin are built with scripts. And the way scripts work is you write some code using Bitcoin scripting language, and you basically take the bytecode of that and hash it, and that hash is your address. What I think is so cool about this, and why it's I think a really interesting part of blockchain history, the introduction of scripts is like Bitcoin introduced digital money, but these scripts introduced the first time that assets could be owned by computer programs. Before, like, public key is a lot more related to just a single person, but now I can write some code that says, hey, like, nobody can move this money until a certain point in time, or until somebody provides the hash of something, and there's no way you can kind of move that money. A computer program owns that money. So how does the script how does that work? How do you create the script? If you're used to kind of smart contracts on Ethereum, on most blockchains, this is a little bit different. When you create a script, you write the code, compile your script into some bytecode, and you just hash it. You don't need to deploy any bytecode. You just get the hash, and you can transfer some Bitcoin to it. You're never up until this point, like, people might not even know if these coins are owned by a script or by a normal account. It's just sent to an address. The way you run a script is, if I'm trying to spend some coins that have been sent to a script, in a Bitcoin transaction, you're going to include all the coins that are part of that transaction. But if those coins are owned by a script, you need to include the script bytecode. So I need to say, hey, this address is actually a script, and here's the full unhashed bytecode of it. And also here's some inputs. So for example, if this is a multi-sig, I'm gonna provide the bytecode for the multi-sig, and I'm also going to provide all the signatures. So it's going to check that these signatures are valid. And I'm going to include all this data in my transaction. We're still not storing anything on chain. We haven't changed the Bitcoin state at all. The Bitcoin state is just UTXOs and owners. Those owners are just addresses. And this is a bit different than how Ethereum and how kind of most newer smart contract chains work. On Bitcoin, you can't publish any code. You can't store arbitrary data on chain. There's just coins in accounts. On Ethereum, when Vitalik and gang came and made Ethereum, they said first they kind of switched from UTXOs to an account-based model. But then they said, we're going to let you make programs. We're going to let you store those programs on the blockchain itself. So everybody has the bytecode. People don't need to kind of know the bytecode. And Ethereum also added this idea of contract storage. So it's basically saying not only can you make computer programs and store those computer programs on the blockchain, but those computer programs have a hard drive that they can write to. So what we're trying to do at Fuel is to take some of the simplicity of Bitcoin and combine it with the power of Ethereum, the power of modern blockchains, and that enable us to build all these really cool, interesting things. So the Fuel virtual machine ends up looking a little bit like a mix of the EVM and Bitcoin, and I think that's one of the things that makes it so cool. So if we take this the scripts that we've talked about, I don't think I talked about this acronym. This is pay to script hash. That's basically the type of input where you use a script in Bitcoin. So we take this idea of like stateless scripts from Bitcoin, but we combine it with the power of like the Ethereum virtual machine, where you can write this Turing complete code that's written in like a real programming language, which is arbitrarily complex. We get predicates. It's important to know, like, a predicate is just an address. When you think of predicate, you can think of it as like just kind of a really lightweight smart account. You don't deploy predicates, you don't create them, you don't spend predicates. People talk about spending predicates sometime, and I kind of know what they mean, but it's a little bit inaccurate to say you spend a predicate. You spend coins from a predicate in the same way, like you don't spend an Ethereum account, you spend the ETH from your account. And because a predicate's just an address, it's not deployed or anything, it's only really useful if it owns assets. Well, a predicate gets invoked when there's an asset that a predicate's holding and it's being transferred somewhere else. So let's look at some examples of a predicate. What are some types of things we could build with a predicate? I couldn't think of a simpler idea of a predicate than this like free giveaway predicate. This is a predicate where it just always returns true. So I guess you would use this predicate if you wanted to just give away some coins. Funny thing is, it's actually not that easy if you wanted to just give away coins on a normal blockchain. I guess you could deploy a smart contract that anybody could call to give it away, but that seems like kind of overkill, right? You're just trying to give away coins. And you could like share your private key, but now you're giving away more than just coins. You're also giving away like the whole account that holds those coins. If you just want to give away any coins, you can make this predicate, which is, again, a predicate's just a single function that returns true or false. And if it returns true, then that basically allows the coins held by that predicate to be spent. So let's go to a little more complex example. Maybe a predicate where you want people to solve some riddle. You basically say, hey, I posted some riddle online, and if you come up with the answer, you can give that answer, pass the answer to this predicate as like the parameter of this predicate. And if you got the right answer, then it's going to return true and you'll be able to take the coins. So what this code is doing here is it's just checking taking an input of a password and checking the expected hash against that input. Now, I wouldn't recommend this in practice. As soon as you do this once, the secret password is revealed to the entire blockchain, but this is a primitive way of doing that. A real world example, something we actually do use predicates for at Fuel, is account abstraction. Now, I know account abstraction is it's a total buzzword these days. It means a lot of different things to different people. But ultimately, what account abstraction is it's not having the blockchain enforce what it thinks an account is. It lets the developer choose what is an account, what are the rules for that account, how does that work? Now, on most blockchains, account abstraction is often being handled with with smart contracts. We have a lot of smart contract wallets, which are great. But as we talked about earlier, smart contract wallets add a lot of bloat to the chain. They add a lot of state. They add a lot of overhead. I think this is one of the reasons that smart contract wallets haven't taken off that much. We've seen multi-sigs like Gnosis Safe being used quite heavily, but people aren't using smart wallets on their day-to-day basis because there's just a lot of overhead and complexity. On Fuel, we can use predicates for our account abstraction. What we were trying to do in this example here is on Fuel, we wanted to support Ethereum wallets. We wanted anyone with their MetaMask or their Rabby or whatever Ethereum wallet to be able to use Fuel, even though that's the Ethereum kind of account mechanism is not the native Fuel mechanism. So all we had to do was make a pretty simple predicate that will validate EVM signatures. So this predicate it's going to take a signature as an input. It's going to basically check that signature is signing the transaction ID, and if that signature is signing the transaction ID, then it's going to get the address that signed it and check that address matches kind of the stored configurable. This is like the constant address that owns this account. So now we've used predicates to make a new type of account where any Ethereum wallet can sign it. And you can do the same thing I think we've also built it for Solana wallets and Bitcoin wallets. And if you want to build this for, Cosmos wallets, if you want to build it for Sui wallets, you can basically support, or one thing we've built at least a demo of is supporting passkeys. You can build any type of wallet. You can build multi-sigs. You can build it using predicates. So yeah, I just kind of went over predicate-based accounts. This is, I think, mostly what predicates have been used for so far, but what else can we do with predicates? Can we build applications with predicates? So let's take a look at some applications built with predicates. Now, I originally wrote all the code for this predicate, and then I kind of put it in this presentation and realized that it was probably too much code to be able to ingest in a simple presentation. So I just wrote some kind of English logic here that, let's say we have a predicate and you send some ETH to that predicate. This predicate will let anybody take the ETH as long as they send 3,800 USDC to me. I guess you can see I made this presentation a few months ago when the price was a little bit lower. This I wouldn't want to use this predicate anymore. I don't want to sell my ETH that cheap. But let's say my predicate says it'll give you any ETH if you give the equivalent amount of USDC to David's address. And there's maybe another condition that says if you are David, then you can also just take the ETH. That basically lets me, I can cancel my own transaction, just take my ETH, or somebody else can take my ETH if they pay me. We've got a diagram of this. If I was building this order book, I would come up with this predicate. I would kind of calculate the address of it on my computer and say, this is a predicate for a limit order that will have the logic I just showed. And I basically open my order by just doing an ETH transfer. I just send some ETH to that address. If someone wants to fill that order, they can take the ETH, but you can see they also have to kind of send the USDC to me. That's me in the hat there. And if I want to cancel my order, I can just take my ETH back. So now we built like a really lightweight version of an order book. We didn't need to write any smart contracts. We didn't need to store any state. We didn't need to deploy any code. Like, this is the simplest way. The only thing that's happening here in these three different types of transactions is just one or two different coins moving around. That's super cool. Another cool thing we can do with predicates are accounts, as we've said. They're just addresses. And that means that they can pay gas fees. So we can build what we call a gas sponsored predicate. So let's say, I built some game. A lot of people want to build games and they don't want users to have to deal with paying gas fees, like having gas in their wallet, whatnot. So they want to sponsor the user's transactions. On most blockchains, you need some kind of complicated paymaster sponsorship system where instead of just sending a transaction, you have to sign a message and send it to some server, and that server will pay the fee and whatnot. On Fuel, we can do something much simpler. I can just make a predicate and send a bunch of ETH to that predicate, and have that predicate set the conditions for what types of transactions it'll pay for. So let's say, yeah, I'm building a Pudgy World. I'm building like a Pudgy Penguin based game for the Pudgy Penguin NFTs. I can make a predicate that will basically only pay your gas fees if you hold a Pudgy Penguin NFT and if you're interacting with the Pudgy World game. So now you're not letting, paying everybody's gas fees for everything. You're saying only a certain type of accounts can get their gas paid for, and it's only for doing a certain type of thing. So those are some examples of kind of some things we can do with a predicate. Now let's take a little bit closer look at predicate and understand what a predicate actually is. So predicates are stateless. We talked before about why this is so important. Building stateless applications is how we make blockchains sustainable. And by being stateless, it means it's somewhat limited compared to a smart contract. It can't read data that's stored on the chain. So it can't read data from smart contracts. It can't call a smart contract and look at get the data that's returned from it. Can't really look at the date or time. We do have kind of a workaround There is a way that you can build kind of time-bounded restrictions on predicates, but from the most hand, it can't get the exact date and time or the exact block number that a predicate that a transaction is in. And I know this is restrictive, but one really nice property that predicates give us is that once a predicate evaluates to true, then it'll always evaluate to true within the context of that transaction. If I show you a transaction and I send a transaction to your node and your node kind of looks at my transactions as the predicate's true, it knows that predicate will always be true unless the transaction changes. And this is not true with smart contracts, because I could create a Uniswap trade and send you a transaction for a Uniswap trade, and your node can say, yeah, this trade looks good. This will totally complete. But by the time I actually send the trade, the price has moved on Uniswap, and now the trade fails. So this is one way that predicates kind of give us some nice scaling properties, because the nodes don't need to keep rerunning this code. So I said everything that the predicate can't access. It can't access state, things like that. What it can access is everything that's part of the transaction. So first of all, predicates have input parameters. The user can kind of pass in things like, we had that example where they pass in a password or where they pass in some signature. The predicate can also look at all the input coins in a transaction. They can see not just coins that are owned by the predicate, but coins that not just coins owned by the predicate, but coins owned by any account that are included in the transaction. And it can look at output coins. It can see where are coins being sent in this transaction. And finally, it can look at the script of a transaction. If you're not familiar with the script is basically what smart contracts are being called, what arbitrary logic is being run by the transaction. And by being able to look at the script, that's how we can restrict things like restricting the transaction to only interact with Pudgy World or something like that, to interact with a specific smart contract. The other thing about predicates is that they're executed at the beginning of a transaction lifecycle. So the way a node processes a transaction on Fuel, it's going to first check that all the inputs to a transaction exist. It's going to check the accounting, make sure the inputs, that you're not putting 1 ETH as an input and 10 ETH as an output. It's going to check normal accounts, and then it's going to run all the predicates. Those are kind of like the pre-execution checks. Only then, after all this has been validated, and again, steps 1 through 4 only need to be run once, then it'll run the script, which is like all the smart contract calls, all the stateful things. And as I said, step 5 is the one that needs to be rerun, as the state of the blockchain changes. Common question again about predicates: are predicates intense? Short answer is no. Predicates are not intense. They do have some similarities. Intense and intents are a super cool, area. Intense is basically taking the idea of a transaction and making it more flexible. That, a transaction is very specific about what it wants done. An intent says it only specifies the end state. It says, I don't care what you do in this transaction, but I know by the end of this transaction, I want to have at least, 4,000 USDC, and I'm willing to give up at least 1 ETH. Predicates are kind of the account version of this transition. Public key / EOAs are very rigid. Predicates are more flexible. They're more programmable. They put more power. Predicates and intents both put more power in the hands of the developer to build more expressive applications. So predicates are not intents. However, predicates can be used to build intent-powered applications. This is something we're working on a bit with right now with teams who are building limit order books using predicates, where the predicate's basically an account that will enforce intents. It'll validate various intents. So I've tried to explain so far kind of the high level of what a predicate is, what it can do, what are some simple things you can do with it. For the kind of next and kind of final section of this talk, I want to kind of go into the more area of research of where with the cutting edge of what we're exploring with predicates. We've shown that you can build, account abstraction. You can build different types of wallets with predicates. We've shown that you can build limit orders. You can build kind of some cool, simple applications. But could you build Uniswap? Could you build Aave? Could you build full applications that normally would need a smart contract and build them with just predicates? The answer is probably, basically. And the way you do this is through a technique called state rehydration. We've said that predicates are stateless. They do have access to the coins that are part of a transaction. That is in some sense a type of state, but they don't have access to state in the same way a smart contract does. But we can use a technique where as long as we have access to some bit of information, like the address that holds a coin, and we can store some data in that address, we can include the full rehydrated state. We can include a bunch of data, a lot more data, and basically hash it and check that hash matches some commitment that's stored on chain. Predicates are already some form of state rehydration in the sense of predicates are just an address that owns a coin. And whenever we want to use the predicate, we can create a transaction that includes the script of a predicate, attach it to a coin, and we're essentially rehydrating the full code of this predicate. But what if we could take this idea further and not just rehydrate the bytecode, but also rehydrate the state? This is a design that we're working on where you basically, instead of storing all the data of an application on the chain itself and making every node in the network track all that data, you can just kind of store a hash of it, a commitment, and basically log the full state of a predicate, make indexers track the full state. So, the state does still need to be tracked somewhere, but we put it on various indexers to track it. And indexers we don't have the same decentralization requirements in indexer. And we can let users ask block builders to basically rehydrate this data. The user can go to a block builder and say, hey, I would like to trade in this predicate-based version of Uniswap. Can you get can you rehydrate the state for me? Can you get that data from somewhere else and include it in my transaction? And if you do, I'll pay you a fee. So there's a few different techniques you can do that you can do this with. You can look at the asset ID of a UTXO, and on Fuel has native assets, so you can kind of include a little bit of arbitrary data in an asset ID. You can also look at the predicate that holds a asset. So these are kind of some different ways that you can include a state commitment on chain somewhere and let a predicate validate that. So the way you would do this would be maybe you have say we're trying to make Uniswap using just predicates. We would put the state elements. This is generally the elements of a Uniswap V2. You have kind of two different assets. You've got some reserve balances, total liquidity. We would take this state and put it in the configurables. Configurables are the equivalent of like an immutable variable in Solidity. And instead of changing these values every time there's a trade, we would just move a UTXO around from these like pool state predicates. And whenever there's a trade, there's kind of this NFT. that moves from a predicate with one state to a predicate with another state. So here where there's some trade that's happening, some user traded against a pool, and now the reserve of this pool is trading from 10 and 5 to 12 and 4. But we're not actually storing that 10 and 5 or 12 and 4 on chain. We're just there's just one UTXO that's kind of acting like a chip on a roulette board. My next slide, I even have a roulette board. You can think of this as like a chip that's being moved around to represent the state. So that sounds super complicated. Again, this is kind of the cutting edge of what we're exploring. But why would you do this? Why would you build something so seemingly complicated on the surface when we already have working smart contracts? The goal of this is to build sustainably fast blockchains that give the performance that everyone's looking for. We're obviously getting to a world where we have Solanas and bases and these really high performance chains which users and developers really demand, but these chains are very unsustainable. It's hard to run a node. It's hard to gather data from them. The nodes become bigger and bigger and bigger, and as they become bigger and bigger, we just enter a world where only kind of the wealthy companies, large companies can actually run these nodes. And the reason at least for me, the reason I got into this space in the first place was to give power to the people, to take power away from the large institutions and let everyday people contribute to these networks. That's what we're trying to build with Fuel. We're trying to build a system where we can have all the performance we need, where we can build a really high throughput, high velocity on-chain economy, and still have the values of Ethereum and Bitcoin, the values of decentralization. So that's our mission at Fuel. Hope that was interesting. I know again, predicates are a tough thing to wrap your head around, but hope that was interesting, and would love to open to any questions if you guys have any.
Yeah, definitely was very interesting. Let's open the floor for discussion. If you have any questions, feel free to pop them in the chat. Adam is saying earlier you mentioned the Bitcoin scripting language. Can you explain this a little more? Is this similar to bytecode or something more readable by humans?
Great question. I'm actually going to pull up in an earlier version of this presentation. I actually showed some Bitcoin scripts. Let me just show that again. So this is in this kind of different version of the same presentation, I talked about Bitcoin scripts. This is actually what the Bitcoin scripting looks like, or at least one tool of it. So there is a programming language. This here is the code for building multi-sig on Bitcoin. I know it's barely readable. This is the Bitcoin script code for building I think this is a state channel. This is some kind of like lock function. You can see it's validating a block time. So yeah, Bitcoin has this very primitive, very kind of confusing programming language. You would write these types of scripts, compile it to bytecode, and then that is a Bitcoin script. So our goal with Fuel was to build something that had some of these properties of Bitcoin scripts, which we think is a really interesting model, and a model that's really hasn't been used by other chains outside of Bitcoin, but do it in a way that it's not limited to these clunky scripts here, a way that you would have like all the flexibility and expressivity of Ethereum and other blockchains. Does that explain it, or? Awesome. Are predicates always Boolean? Yes. So predicates are always return true or false, and that returning true or false is basically saying, is it valid or not? If I have evaluated a transaction, can the coins of this predicate be spent? And that's just a true or false. What are the limitations of predicate other than state? Good question. State is definitely the big one, that you can't read state, write state. I think one other limitation, mostly in developer experience, predicates, since they are stateless, they also can't log events. So again, this is mostly like an issue developer experience when you're building things with when you run into issues with predicates, it can be a bit frustrating to debug the issues with them. This is definitely something that our team is working on addressing to provide kind of some tooling to address that. But I'd say those are the main limitations. I'm trying to think if there's anything else. So yeah, no reading state, no writing state, no logging events. Yeah, I think that's pretty much it. What applications definitely cannot be built with predicates? At this stage, I'm not sure. Theoretically, I think you could probably build everything with it. There are some little there are some changes that would need to be made to the Fuel VM. You might not be able to build every application today. Like one thing, for example, is a lot of the more advanced examples I showed required having an asset moved around, kind of like an NFT you could think of, like a single UTXO that moves around to represent basically a state commitment. Right now on Fuel, only smart contracts can mint assets. You can't really mint an asset from a predicate, but that's one feature that will probably be added at some point. At that point, I don't know. I'm not convinced that once we kind of add those features, I'm not convinced there's anything that you can't build with a predicate. In the short term, though, there's definitely like, it can be at least very hard to build more complex applications. Can there be predicate to predicate compute communication? Not in the traditional sense that you would think of, in the sense of like, like one smart contract calling another smart contract. However, a predicate could be aware of another predicate. A predicate can basically assume, let's say there's a transaction, and there's two input coins. Both of them are owned by different predicates. The predicate can assume that another input owned by another predicate is valid. It can assume that that predicate did execute successfully. So in some sense, if a predicate is aware of another predicate and it's aware of a coin, there's an input that's coming from a predicate that it's aware of, it knows that that predicate did execute successfully, because if it didn't, then the transaction will just fail. Are predicates more vulnerable to collision attacks? We only need to match the smart contract hash, and we can cycle through various permutations of malicious code until we hit a predicate with coins. Interesting. I don't have a exact answer, but just that account hashes are 256 bits, and I think the risk of any collision with a hash that large is incredibly unlikely. So I don't think there's any concern of collisions. It's basically just as vulnerable as private keys, right? You could kind of mine new predicate addresses, but you can also mine new private keys, which generate public key addresses. Do you have any research docs you could share to learn more about predicates? Yeah, docs.fuel.network is our main documentation site. There is some things about predicates there. Outside of that, yeah, I'm not sure. I know predicates is something that we don't have as many resources as we would like. I know we want to be developing more documentation resources around predicates. But yeah, I think if I or anyone else on our team kind of knows some other good resources, we'll maybe send it to Neven and kind of share it with them.
Cool. Looks like this is it. Oh, one more.
Building stateless applications, how to make blockchain stable. I think so. I mean, if you think, there are really like three resource constraints of blockchains. There's the data availability or bandwidth. That how do you ensure that the data of transactions, of state transitions is propagated to a full network. That's been kind of the bottleneck, at least in like the kind of roll-up space for a long time. But we now have 4.4 on Ethereum. We've got DA layers like Celestia, and I saw Avail launch today. So I would say that data availability is a solved problem. Another constraint is execution, which is just how quickly can you run through, can you execute a transaction? that is generally solved with like general computer science things. This is a lot of the work that we've done at Fuel so far, is building a really efficient virtual machine that's much more efficient, that can be executed more quickly than the Ethereum virtual machine. This is also what projects like Solana have done. They've built very performant virtual machines. So we've increased execution a lot. But we're seeing that state is like the other issues. Storing data, taking up hard drive space on every node in the network is something that's really becoming an issue now that we've really addressed those other two issues. So this is being discussed a lot in the Ethereum space. Solana has come out with, not Solana itself, a Solana team has come out with a method for addressing state, which actually bears a lot of similarities to kind of our state rehydration technique. So yeah, I think it's clear that this is a major bottleneck of blockchains. And when you have these kind of bottlenecks constraints, you can either kind of directly solve the issue, with kind of new techniques and new mechanisms. And if they're not solved, you usually just get centralization, right? Like issues in blockchains can be mostly solved by just running one big computer, but that's not how we want to solve it. That's the non-sustainable way to address these issues. So that's why we think this is such an important problem to address, because we don't address it, we just end up with a couple banks, a couple big tech companies running the full nodes.
Okay, I think there are no more questions. So I think we can slowly wrap it up. Guys, if you have any more questions, now's the time to ask. Until then, David, any final words of wisdom for the audience?
No, but thanks so much for joining in. I hope you guys got as excited about Predicates as I did. Yeah, feel free to reach out to me or to the rest of our team with any questions. As I said, I know Predicates are a complicated, just a complicated idea to wrap your head around. But if you're really curious about it, we'd love to help you guys and get you guys up to speed so you can build really cool stuff.
Amazing. Thank you once again. And everybody else, we'll see you on Friday at the same time for the final session in this series. Thanks once again, David, and have a lovely rest of your day.
Thank you. See you guys.
Bye-bye.
Bye.